All right. Hello, everybody. I'm going to go over our midterm review so that we know what's going on and that we're ready for our test. Okay, so to start off, it's talking about a profitable blueberry field. Optimal blueberry growth occurs within a soil pH of 4.5 to 5.0. A blueberry farmer had the soil from a field tested. The results indicate that the hydronium ion concentration is 1.0 times 10 to the negative 8. Hydronium ion is H3O plus. If we are at 10 to the negative 8, so whatever this number is, that tells you what the pH is. So pH is 8. All right. One way farmers can optimize their soil for blueberry growth is by adding elemental sulfur. Okay, equation 1 shows this, where it shows the sulfur combining with oxygen and water, and it turns into H3O and some sulfate ions. Which two indicators, when used independently, would provide results that together are suitable for evaluating soil pH to ensure optimal blueberry growth? Okay, soil pH, optimal blueberry growth. We know that's between 4.5 and 5. We want a combo that's going to tell us if we're close to 4.5 or 5. All right, off the bat, alizarin yellow, that's 10.2 to 12. That's no good. That's not specific at all. B, bromcresol purple, 5.2 could work. If it's below 5.2, that would be pretty good. And bromphenol blue, that's 3 to 4.6. So if it's this would tell us if it's above 4.6, and the purple, that would tell us if it's below 5.2. So that might be good. Bromphenol blue, which we just said, yeah, 4.6 or higher. And Congo red would tell us if it is higher than 5. Methyl red tells me that if it is, well, this is between 4.4 and 6.2. That's not that specific. And alizarin yellow we don't like for this. Okay, so this would tell us if it is, we want it between 4.5 and 5. So this would tell us if we're higher than 5. But it isn't really specific in the middle here. So yeah, I'm not a fan of this one. And for that reason, I'm going to have to choose this. Okay, because this tells us both if they're above, but this one gives us a good range. So if it's less than 5.2 or higher than 4.6, that is basically right around, it gives us the middle, that middle range that we want. Okay, number 2. Which row in the table completes the claim describing a possible cause and effect of adding elemental sulfur to the soil? Okay, we know that adding the sulfur will make H3O. So first of all, it's going to increase the hydronium, and that is the cause. When you increase hydronium, you will then decrease pH. So hydronium, we know hydronium is made by acid. And we know that the pH scale, so times 10 is 1 step on pH. So we do times 10 times 10 times 10. That gives us the 1,000. And that is 3 steps on the pH scale. And it's decreasing because it's getting more acidic. I'm sorry, I didn't realize we couldn't see. I'll go over it again. Hydronium is made by acid. It's times 1,000 because we know from lab last week, every step on the pH scale is a times 10 change. And so since there's a change of 3, we also know it's decreasing because we're getting more acidic. Okay, number 3. Identify one product from equation 1 that supports the claim that adding sulfur increases soil acidity. This should also say acidity here. So a product, okay, we got H3O and we got sulfate. Well, the product is our H3O plus. We know that acids make H3O plus, which are our hydronium ions. Okay, acids make H3O plus. So adding S makes soil more acidic. Right. Honestly, you could probably just leave it at acids make H3O plus as well. All right, moving on. The use of elemental sulfur can result in over-acidifying the soil using ammonium fertilizers such as ammonium sulfate. So this is ammonium, this is sulfate. Is an alternative, reduces this risk. The equation below demonstrates two ways in which ammonium ions contribute to soil acidification. Identify the acid and the base when both water and ammonium fertilizer are added to the soil. Okay, water and ammonium. That's ammonium, that's water. We're looking at equation 2. Identify the acid and the base. Compare the pattern of behaviors to identify or to explain why each is classified as such. Okay, so acids, we know, give H. Bases, we know, take H. So let's find NH4. Let's find what it turns into. So NH4 turns into NH3. That gave away an H. So NH4 plus is our acid, and water turned into H3O. Water took an H. So that's water. So comparison of behaviors, you would say NH4 donated a hydrogen while H2O took a hydrogen. Okay, and that's why. That is their behavior. That's what they do. Okay, how many grams of nitrogen are added? Sorry, I'm grabbing a periodic table. I'll reread it in a moment. Okay. How many grams of nitrogen are added to the soil when 100 grams of the substance that acidifies soil with reduced risk is applied? Okay, so a little silly phrasing here, but the way they like to phrase it, I guess, is that you need to comprehend what you're reading. The substance that acidifies soil with reduced risk, ammonium fertilizers. So we're talking about this. NH4 2SO4. So that is that. And there's a bit of stoichiometry to be done here. So we are talking about NH4 2SO4. So we're adding 100 grams of that. So we need, unfortunately, we need the molar mass of this. So there are 2 nitrogens, there are 8 hydrogens, because there's 4 times 2, right? 1 nitrogen times 2. There's S, 1 S, and 4 O's. So check out your reference table. Oxygen, mass of 16, nitrogen, mass of 14.01, sulfur, mass of 32.06, hydrogen is 1.01. That's where I'm getting all those numbers from. Times 1.01 times 14.01 times 32.06 times 16.00. And multiply this, you get 64. This 32.06, sorry, that should be equals. This will be 8.08. This will be 28.01. Then we gotta add them all up. So 8.01 plus 8.08 plus 32.06 plus 64. Add it all up, it's 132.15 grams per mole. All right, so now we know there's 100 grams of this stuff. So we got 100 grams of NH4 2SO4, this whole thing. And we know that in 1 mole there is that many grams. Right, because remember, we're trying to end up with moles. Okay, so we do 100 divided by that. Right, 100 times 1 is 100 divided by this. Gives me 0.7567 moles of NH4 to SO4. All right, so now I have the number of moles of that. And so if I have this many moles of that, well, in here, in one of these moles, I have 2 moles of nitrogen, right? In one molecule of this, there's 2 atoms of nitrogen. So I'm going to do this, 0.7567 moles of our compound times, we know in 1 mole of the whole compound, there are 2 moles of nitrogen atoms. So times 2, that gives me 1.5134 moles of nitrogen. And remember, the question is asking for grams of nitrogen. So now we're going to do 1.5134 moles of nitrogen, and I know that 1 mole of nitrogen is 14.01 grams. So that gives me that times 14.01 gives me 21.20 grams. Whew. Tough one. Glad that answer was there. It would have been awkward if I did all that wrong, huh? All right. So it's all this. I'll post it. Moving on. 6. Cite numerical evidence from equation 3 to demonstrate the claim that atoms and therefore mass are conserved. Conserved means kept the same. So in equation 3, conservation of mass, that is why we balance equations, right? So you can see over here on the left hand of the equation, there's 1 nitrogen, then 1 nitrogen, 4 hydrogens, 2 plus 2, 4 hydrogens, 4 oxygens, 3 oxygens plus 1, 4 oxygens, right? Your reactants just get rearranged into your products. So I will say there is, R, because I'm talking about more than one thing. There are 1 N, 4 O's, and 4 H's on either side of the equation. Okay. 7. Explain using Le Chatelier's principle and equation 2 for evidence how the excessive use of ammonium fertilizers could lead to soil acidification. So Le Chatelier's principle has to do with equilibrium. If you remember what we learned that right before spring break. That is when if you add something to one side of the equation, it will shift to the other side. And then if you remove something from that side of the equation, it moves towards that side. So excessive use of ammonium fertilizers. So that means we're adding a lot of NH4. If we add a lot of NH4, we shift the other way, we will end up with more of this side. And look at that, H3O's on this side. That makes stuff acidic. So explain using that, So I will say adding NH4 will shift equilibrium right, making more H3O plus, which is an acid, or like which is acidic and which acidifies the solution. You could say something like that. All right, equation 2 again. Which of the following disturbances to the equilibrium system would increase NH4 dissociation? So dissociation means splitting into ions. And that's what NH4 does in this equation, right? So it might not look like it, but NH4, what's happening, as it goes this way, it is losing a hydrogen. It's dissociating with that hydrogen. This is what adds on to water to make H3O. So going right increases dissociation. And that's what we're looking for. So leaching NH4, removing NH4, no, if we remove from the left, it will pull to the left. So it's not this. B, adding water to the soil. If we add to the left, it will go to the right. Yeah, so that is what will shift it to the right. So it is B. If you look at the other ones, it would, you would process of elimination it, I guess. Removing water from the soil, if you remove from the left, you pull towards left. Adding NH3 to the soil, if you add to the right, you go left. And test taking tip, if you know Le Chatelier's rule, but you're a little confused as to exactly what, if you notice that all of them are going to pull in one direction and there's only one choice that pulls in the opposite direction, that's got to be your answer, right? Okay. Moving on. Hard water and water treatment. Hard water is a label commonly used to describe water that has a significant concentration of dissolved metal ions. Hard water can leave a film on your skin after a shower because soaps and oils do not lather and rinse as easily. Magnesium and calcium are two offending species in creating hard water. The process of water softening uses substances that precipitate dissolved minerals. Many rural water treatment plants add hydroxide, OH, and carbonate to the water supply. These ions react to form insoluble precipitates that settle to the bottom of the tank where they can be removed by filtering. Okay, we have an equation and blank products. So A, determine the products of the precipitate forming reaction. Okay, well we know it forms a precipitate, but let's make our products first. You got two compounds, two ionic compounds. This is a classic double displacement. Calcium is going to grab the hydroxide ion. Sodium is going to grab the chloride. So here, you need to drop and swap. So we know Na. Okay, Na is group 1, needs to go 1 backwards. So it's a +1. Cl needs to go 1 forwards, gets group 18, so it's a -1. So since I'm just going to do the drop and swap right here, I guess. Yeah. Na +1, Cl -1. You drop the 1 and the 1. It's just a 1 and a 1. So it's normal. Then we have CaOH. This is a polyatomic ion. Hydroxide, OH-, right? It acts like one thing. So we are going to have calcium, which we see group 2, so back 1, back 2, so it's a +2. Calcium is a +2. Hydroxide is a minus, and you should always put parentheses while you're doing your drop and swap. Because if there's anything other than a 1, you need parentheses, and this helps you just remember that it's one thing. The 2 goes outside the parentheses, the 1 goes here. So you get Ca1, but you don't need to write that. Ca1, parentheses, OH, close parentheses, 2. You need 2 hydroxides, each with their -1, to pair up with calcium that has a +2. Okay, B, add state of matter indicators to each product according to the solubility table in your reference tables. Okay, well this reaction is precipitate forming, so we know one of them will be solid. Right, the precipitate is the solid that comes out of your reaction. So we go do our reference tables. Flip, okay, not here. Oh, selected ions forming aqueous solutions. If it is on here, it is aqueous. Group 1 metals, Sodium, ding, ding, ding. Right, group 1, sodium is group 1 because it is in group 1. So this will be aqueous, dissolved. And since this is not here and we know it forms a precipitate, this is your solid. And C, ensure that the equation is balanced by adding any necessary coefficients. Okay, well, let's see. I have 2 OHs over here. I have only 1 OH here. I have 2 chlorines over here. And only 1 chlorine here. Okay, well, let me fix the chlorine. So I'll put a 2. So now I have 2 chlorines, but now I also have 2 sodiums. So I'm going to put a 2 here. Now I have 2 sodiums and 2 OHs. Oh, but that's what I want, right? Okay, so that's good. 2 OHs, 2 NAs, 2 chlorines, 1 calcium. Balanced. So this question has a lot going on with it. It includes a lot of different concepts that we've covered. All right, moving on. If water treatment plants do not use hydroxide and carbonate to remove these ions from our water, they can lead to pipe scaling, in which precipitates form on the inside of household plumbing. So like in your pipes and stuff. Use data from the solubility curves to make a claim about which substance, calcium chloride or calcium hydroxide, is less likely to cause scaling in home plumbing. Okay, well, if it is going to cause scaling, it will precipitate. So precipitates are solid. They do not dissolve well. So this one is really bad at dissolving. Look at those tiny numbers for the grams of solute that can dissolve in 100 grams of water. So this one is most likely to be the solid. Right? This will be a solid precipitate. But it's saying which substance is less likely to cause scaling. So less likely means that it will stay dissolved. So the one that will stay dissolved is calcium chloride. How do the solubility curves support this claim? It has a much higher solubility. So it will stay dissolved and not precipitate. Yeah, that scaling is something if your home has hard water, that means that you will get like a white film if like water evaporates, let's say. Okay. A solution containing 140 grams of calcium chloride dissolved in 100 grams of water at 80 degrees. Okay, it's dissolved in 100 grams of water. That's just what this table is talking about. This is grams of solute per 100 grams of water. So nothing we need to worry about here. 80 degrees, 140 grams. Let's see. 80 degrees, 140 is here. We are under the line. If you are under the line, you are unsaturated and you are homogeneous, right? You have a completely a solution with everything dissolved, and you're under the line. Saturated would mean that it is on the line or above. Supersaturated would be if it's above the line and everything is still dissolved through some other manipulation. Heterogeneous means that you can see the different parts of it. So heterogeneous and saturated well, if you have a heterogeneous solution, it is saturated, because that means like you added calcium chloride and then you went beyond and then you have some staying solid. But under the line is unsaturated, at or above the line is you're saturated. Okay, what is the maximum amount of calcium chloride that can be dissolved in 300 grams of water at 60 degrees Celsius? 300 grams. All right, well, first of all, 60 degrees Celsius, we can fit 137 grams of calcium chloride in 100 grams of water. So that's 137 grams. But remember, this is in 100 grams of water. We have 3 times as much water now. So we're going to multiply by 3. And so you take 137 times 3, you get 411. 411 grams. Put your unit, need your unit. All right, titrations, gotta love them. The titration was performed to determine the concentration of a sample of hydrochloric acid. The titrant chosen for the task was a 0.2 molar solution of sodium hydroxide, NaOH. The recorded data for the titration is given to the right. Okay, so we got all our data here. First of all, write a complete chemical equation below for the reaction performed in the equation. Or this should say in the titration. And this is a neutralization reaction, right? So we're going to have HCl plus NaOH. This we know, acid base, H combines with OH. You make water, which should be liquid, and NaCl, which would be aqueous. Metal comes first. Technically, you should drop and swap just to check, but we know sodium chloride is that formula. Okay, construct a mathematical representation to calculate the concentration of HCl determined. Well, we gotta use our formula for this. MaVa equals MbVb. Molarity of the acid times the volume of acid equals molarity of the base times the volume of base. So the volume of analyte used, so the acid is our analyte because we don't know about the analyte. We don't know Ma. We know that there were 10 milliliters of it used. We do know Mb, that's our sodium hydroxide titrants. That's 0.2 molar. For Vb, you gotta figure out the volume used. We gotta interpret this. So final volume 15.1, 15.2. I'm calling it 15.24 milliliters. Initial volume 1.1, 1.2. This looks like right before the 1.3, so I'm calling it 1.29 milliliters. So the volume used is Vf minus Vi. So we have 15.24 minus 1.29. Gives me 13.95 milliliters. That's what you put in here. Okay, so we got 0.2 times that. Gives me 2.79 molarity times milliliters equals Ma times 10 ml. Divide by 10 ml, divide by 10 ml. The ml's go away, the whole 10 ml goes away over here. You get Ma equals 2.79 divided by 10. You get 0.279 molar. Okay, next, it says explain how the proportions of reactants would differ if a base such as calcium hydroxide, CaOH2, were to react with HCl instead of a base such as NaOH. So, as we've been seeing, we know that OH grabs H, right? OH grabs H. Well, calcium hydroxide has 2 OHs, right? So HCl, if these are going to react, one HCl will not satisfy this. You are going to need 2 HCl's. So that's what I mean when I say the proportions of reactants would differ. So we would say there would be a 2-to-1 ratio of HCl to CaOH2 because every CaOH2 could accept 2 two H pluses and HCl only has one H plus to give. There are acids, so HCl is what we call a monoprotic acid because it has one proton, whereas there are things that exist like sulfuric acid. Sulfuric acid is H2SO4. That has two H's it can give. Sulfuric acid is super acidic because it will give away two hydrogens. All right, so that's the test. Should be doable. It's difficult, combines a lot of concepts, yes, but it can be done. I believe in you all. Good luck studying.